The James Webb Space Telescope has recently captured something deeply unsettling near one of the largest black holes ever discovered, TON 618. What it observed has left scientists both astonished and baffled. Instead of chaotic, random energy, as expected, Webb detected pulsing patterns of light that seemed deliberate, structured, and rhythmic. These emissions are emerging from a region where, according to all known physics, light should not exist. At the very boundary of one of the most destructive forces in the universe, there appears to be order, a beat, a pattern, possibly even a message. The implications are profound. The data is real. If the interpretations hold true, this could force humanity to rethink everything we know about black holes, space-time, and the very nature of reality. The James Webb Space Telescope, designed to peer deeper into the cosmos than any telescope before it, was expected to reveal the faint signatures of the early universe, distant galaxies, infant stars, and the residual warmth of ancient worlds. But nothing could have prepared researchers for what it discovered at the edge of TON 618. At first, the telescope picked up standard high-energy bursts. But soon, a pattern emerged. Sharp energy spikes rising and falling near the event horizon, the region where light and matter are believed to be forever lost. What was most striking wasn't the violence of these flares, but their organization. The energy seemed to pulse with a rhythm, almost like breath. "It's like something is alive at the edge of nothing," one scientist remarked. Within hours, observatories across the globe began to reanalyze their data. What they found wasn't just consistent with Webb's results, it confirmed them. TON 618 wasn't simply swallowing matter in chaotic spirals, it was emitting a signal. Something massive, ancient, and previously thought to be silent was now behaving like a system, perhaps even a mechanism, with remarkable precision. This wasn't just a black hole, it was doing something unexpected. It was communicating in a language yet to be understood. To understand why this is so significant, one must first understand TON 618. This isn't an ordinary black hole. It's a true behemoth, estimated to have a mass 66 billion times that of our Sun. If it were located at the center of our solar system, its event horizon would stretch far beyond Pluto, engulfing every planet and then some. But its enormity isn't its only remarkable feature. What makes TON 618 even more fascinating is its distance. Located nearly 10.8 billion light-years away, the light reaching us now left before Earth even existed. We are looking into a deep, ancient past, at a black hole that formed when the universe was just a few billion years old. It is both a relic of the early cosmos and an anomaly that defies conventional black hole growth theories. Before the James Webb Telescope, TON 618 was more myth than reality, too distant to resolve in detail, known only by its gravitational influence on nearby galaxies. Webb changed all that. With its infrared sensitivity, it detected energy not just around but seemingly right up to the event horizon. Even more shocking were the characteristics of the signals themselves. They weren't wild or sporadic. They were regular, timed, structured. This contradicts current models, which state that the more massive a black hole is, the slower and less active its observable emissions should be. But TON 618 pulses like a cosmic metronome, blinking at us through space-time in 67-minute intervals. As researchers dug deeper, they found that these pulses weren't just regular, they were evolving. Their shapes, intensity, and timing shifted, subtly from cycle to cycle, showing complexity and internal logic. Artificial intelligence systems were deployed to sift through the data, and what they uncovered was extraordinary. Harmonic sequences, echo-like reverberations, and patterns resembling resonant feedback loops. The structure of the signals suggested not just repetition but purpose. Waves shaped by something, perhaps by the geometry of space-time itself, or by unknown forces at work near the black hole's edge. Some theories proposed magnetic reconnection, events where twisted fields snap and release energy in bursts. Others explored the possibility of gravitational echoes, reflections of energy bouncing within the warped space-time. Still, none of these ideas fully explain the observed symmetry and timing. A radical suggestion soon emerged. What if these emissions weren't natural? What if they were the result of quantum-scale feedback mechanisms, particles interacting across time, not just space? This idea ventures beyond even cutting-edge physics, but the data remains stubbornly clear. Whatever's happening at TON 618, it's not random. The most unsettling part of the discovery isn't even the signal's complexity, but its origin. The pulses are emerging from regions that, according to our current understanding, should be unreachable. The event horizon is the ultimate boundary in nature. Once crossed, not even light can escape. But Webb appears to be detecting emissions either at or just inside this limit. If confirmed, this could shake the foundation of black hole physics. Some scientists are turning to theories like quantum tunneling, or suggesting that the event horizon isn't as impermeable as once thought. If information or light can escape a black hole, then we may be approaching a solution to the information paradox, a mystery that has haunted physics for decades. The implications stretch far beyond TON 618. If this black hole, so massive, so ancient, can defy the rules, then perhaps our entire model of cosmic evolution is incomplete. TON 618 formed at a time when black holes weren't supposed to exist at this scale. Its surrounding region is filled with chemically complex galaxies, far more developed than expected for such an early era of the universe. This suggests that black holes can grow faster and galaxies evolve more quickly than our current models allow. Alternative theories of formation, like direct collapse from massive gas clouds or even remnants of the Big Bang, are being reconsidered. Adding to the mystery, some researchers believe that TON 618's structured energy pulses may reveal new clues about dark energy, the elusive force accelerating the universe's expansion. The emissions exhibit fluctuations inconsistent with gravitational effects alone. If they're being shaped by interactions with dark energy, then we may be seeing the first evidence that it behaves differently near extreme gravitational fields. This could revolutionize our understanding of cosmology, providing insight into how dark energy responds to matter and curvature, instead of just influencing large-scale structure. And then there's the accretion disk, the bright, superheated spiral of gas and dust falling into the black hole. Normally, these disks are violent but predictable, but Webb recorded erratic behavior, slowdowns, localized brightenings, regions that paused and then surged as if responding to some invisible signal. This wasn't noise. The accretion disk seemed to echo the pulses coming from the black hole's core. As each structured flare occurred, the surrounding matter responded, like a conversation between energy and environment. Some physicists now speculate that this could represent a kind of gravitational feedback loop, a dynamic system where information, not just matter, shapes the behavior of the cosmos. To explain this, researchers are now diving into the most extreme edge of theoretical physics, quantum gravity. At the frontier where Einstein's relativity and quantum mechanics collide, space-time may behave like a jittery, unstable foam. In this environment, rules like light cannot escape may only be true most of the time, not always. This could be why we're seeing emissions from regions that should be hidden forever. Webb may be catching glimpses of a universe where location, time, and causality behave differently than we've ever imagined. Not everyone agrees. Some scientists caution that what we're seeing might be a data artifact, or an unusual case of gravitational lensing. Others warn about instrument sensitivity and sensor calibration. But the consistency across multiple observatories, the repeated patterns, and the mathematical symmetry of the pulses point to something real. Scientists from NASA, ESA, and global research teams are now collaborating, using telescopes across the spectrum, from X-ray to radio to gravitational wave detectors, to confirm and expand on Webb's observations. The urgency is growing. The why observations from TON 618 may represent a turning point in astrophysics. International teams are planning coordinated campaigns, including efforts to use the next generation of space-based observatories like LISA and the Einstein telescope. Some researchers are even simulating quantum space-time interactions on Earth using quantum computers to understand how light and energy behave near a black hole's edge. This isn't just an academic debate. It's the dawn of a new era in physics. For the first time, observations are pointing to a reality where our existing theories fall short. Concepts once confined to theoretical speculation, like quantum echo chambers, semi-permeable horizons, or dark energy interactions, are now front and center in scientific discussion. Textbooks may soon need rewriting, and the next generation of scientists is entering the field at a moment where the rules are being questioned and the answers remain just out of reach. What the James Webb Space Telescope has shown us through TON 618 is more than just a black hole. It's a keyhole view into a deeper truth, a cosmos far more complex, intelligent, and active than we ever imagined. We may not yet understand what the pulses mean or what force shapes them, but we are listening. And with every observation, every question, we move closer to the edge of what's possible.